Welcome. I like to present a project about predicting urban development in North Carolina with GIS and machine learning. My collaborators are Jian Lange and Witold Fraczek from Esri. My name is Carsten Lange and I'm an economics professor at Cal Poly Pomona. We have three goals in this talk. One is we want to show the benefits of a multidisciplinary collaboration. Second, we want to show the benefits when working with two different softwares. And we will talk a little bit about possible pitfalls in machine learning. Our research area is in North Carolina. It's called the Tri-City. It's a 80 miles times 50 miles area. We split this area into 30 times 30 meter raster cells. That gives us a total of 4,300 times 2,700 raster cells. With other words, a total of 11 million cells. The research goal is to predict areas or raster cells that changed from non-urban in 2001 to urban in 2016. The idea behind this is if we have a working prediction model, we can use the same model to predict the future. Our approach follows 4 steps. The first step is we categorize 2001 and 2016 raster cells into developed or undeveloped. Then we compare 2001 and 2016 to find out which cells have changed from undeveloped to developed. In step 3, we collect data that potentially can explain urbanization. Then we put everything together and then we use R to develop a machine learning model. The machine learning model is a random forest model and it will predict if a raster cell became urban, yes, or if it stayed non-urban, then became urban will be no. Let's start with step number 1. We got our data from the National Land Cover database, and this database is updated every 5 years. For our research area, for each of our cells, 30 times 30 meters, we have about 20 categories, and you can see them here at the right. We used ArcGIS Pro to recategorize these categories into developed. These were 4 of the original categories. And the rest was categorized as undeveloped, which gives us a total of 2 different classes, developed or undeveloped. Then we go to step number 2 by figuring out, and again, we used ArcGIS Pro, which raster cells changed in which way when we compare 2001 and 2016. There are 4 possible outcomes, and you can see them here. And 2 of these outcomes are not interesting for us. Cells that were already developed, they were already urban in 2001, and they were still urban in 2016. Think about city centers, are not interesting for this research. And few cells actually changed from developed to undeveloped. That might be an industrialized small area that was redesigned back to a natural area. And you can see these were only 2,300 raster cells. The remaining raster cells are relevant for our research. Undeveloped to developed. These are the cells that became urban. They were undeveloped in 2001, but they were developed in 2016. And then cells that were undeveloped in 2001 and still stayed undeveloped in 2016 were categorized as became urban, no. And I want to already get your attention to the very unbalance of our data set. We have about 9 million cells that stayed undeveloped, which makes sense if you think about forests and lake areas and everything. Fortunately, not everything got developed. And some cells, 10,000 cells, became urban. Now in step 3, we have to collect data that potentially can explain urbanization and enrich our original raster cells. We used again ArcGIS Pro for it, and these are the data we considered. but it's probably best to show this to you in ArcGIS Pro. My collaborators, Jian and Witold, used ArcGIS Pro Spatial Analyst extension to record the variables. For each of the cells, the distance to the airport was calculated and color-coded. Highway distance, road distance, drive time to the major cities Durham and Raleigh, distance to protected areas, slopes, population growth, and finally, distance to flat areas. Now that we have these new layers, road distance, slope, and so on, including our layer became urban, yes or no, we have to aggregate all these layers into one layer. You can think about drilling through all these raster cells all the way to the bottom and collecting the data and then writing them down here. Now that we have what we need in ArcGIS Pro, we need to transfer our data from ArcGIS Pro to R. And that is usually a big obstacle when working with two different softwares. But fortunately, there is a tool in ArcGIS Pro and a library that fits this tool in R, both called R-Bridge, that make this process very easy. In fact, there is a dynamic link between ArcGIS and R that makes working with both softwares dynamically at the same time very easy. Here we are in Rstudio in the scripting window, and I like to show you that it takes only 5 lines to connect ArcGIS Pro to a data frame in R. We call this data frame here Data All from Pro. There is something else I like to show you. We do not want to assess the quality of our model with the same data that we use to train the model. Therefore, we split our data in 85% training data and 15% testing data. And only the training data are used to optimize our model, while the testing data that are set aside and are never used for training are used to assess the quality of our model. Now that we have everything in R, it's time to develop our random forest model. A random forest model consists out of several decision trees. Think about submodels. The prediction of a random forest is basically the majority prediction of all these, for example, 500 decision trees. So to understand what a random forest is, it's probably a good idea to start with a decision tree. Here's a mock-up decision tree. A decision tree is basically a tree-like structure where data are led through. And at nodes, there is a decision made if this data record, individual data record, moves either to the left or to the right. So at the end, our data records will end up in one of these final bins. How does it work? Let's say we have a data record, and at the first decision node, the variable drive time is used and the splitting value 27 minutes is used. If the drive time is greater than 27 minutes, then our record ends up down here in this bin. We can see that from the records that ended up in this bin, 83% were non-urbanized and only 17% were developed. So the prediction for every record ending up in this bin would be no. What if the drive time is smaller? Well, then we go to another branch where we analyze the population growth. And let's say the population growth is bigger than 2%. And the distance to the road is smaller than 323 meters. We might end up here. In this bin, 42% of the training records ended up, and 77% of those records were urbanized? Yes. So these cells were actually developed, and only 23% of the cells that ended up in this bin were undeveloped. So the prediction for this bin is yes. Last question we have to clarify is, how does our decision tree come up with which variables to use and which splitting variables to use? The answer is, it uses a training data set, and at each node, it uses the variable and the splitting value that guarantees the best prediction quality for the training data set. So after the training data set has generated the decision tree, we can look at the testing data, lead them through this tree, and make our predictions, and can see how well we did. I did this already in R, and here are the results. The results look pretty impressive. 99.8% were predicted correct. And as we all know, if things are looking too good to be true, usually they are too good to be true. And this is also the case here. If we look at our confusion matrix, well, first, the good message is these are the records or raster cells that did not change from undeveloped to developed. So the majority of the sale, and they were all predicted as no, which is correct. That is great. These are the cells that actually changed in the testing data set from non-developed to developed, and they were all predicted incorrectly. They were all predicted as no rather than yes. So what did our decision tree do here? It simply predicted everything as not changing to developed. And it got this high precision because only such a small amount of cells actually changed from undeveloped to developed. So the error is minor. But the model itself is pretty useless. Why is it useless? Because our training data set was so unbalanced. So we have to do something to better balance our data set. And there is a procedure we used in R. It's called SMODE. And what this procedure does is, from the original majority class, it deletes random records and reduces thereby the majority class. Then it uses a minority class here from our training data set and generates new records that are similar than the old records. Not the same, but similar. For this, the SMODE procedure uses another machine learning algorithm called k-nearest neighbors. And we see we decided to triple our minority class, and now we have these records in our new data set. Here is our mock-up data set again. And with a more balanced data set, it would certainly give us better predictions. However, there are problems with decision trees. Decision trees, although they are very illustrative, are very sensitive when data change. We get totally different decision trees. And also their predictive quality is not very good. What we can do is we can use random forest and just use 500 decision trees and hope to increase our predictive quality. But just using one decision tree and copying it 500 times would not make things better, because the average prediction from these 500 trees would be simply the same predictions we got from a single tree. So our trees have to be different. How can we make our trees different? Since the trees cannot be identical, it means we cannot use the best tree 500 times. We have to use suboptimal trees. In fact, we use trees that are individually not good at all. We call them weak learners. They are very simple and very small. The surprising thing is, if we combine 500 weak learners in a random forest and get their majority vote for classification, we get actually a pretty good prediction. How are these trees different? Well, I said it already. First of all, each tree is very simple, meaning it has only very few levels. Second, at every decision node, a slightly different data set is used. We get these different data sets by drawing from the original data set without replacement after we have the same size of the original data set. That gives us every time a different data set, and this method is called bootstrapping. In addition, at every decision node, not all variables are considered. Only a subset of variables is considered. And the rule of thumb is to use the square root of the number of variables. So if we have 12 variables, we would use at each decision node about 3 variables as candidates for a split. This way, we generate many different decision trees, again 500 in our case. And when all these decision trees are generated independently from the training data, then the random forest can be used to predict. And here are the predictions of our random forest based on the test data. And we can see from the cells that were not developed in 2001 and they were not developed in 2016, so became urban is no, still most of them, but not all, are predicted correctly. And the major change is that the yes cells, the became urban yes cells, most of them are now predicted correctly as yes, and only a small fraction as predicted as no, which is wrong. We can see our accuracy is not that high anymore, but 95% is still a very good accuracy. So after we have our model now and we tested it, that it is a good model, it's time to use it. So we used all our data and predicted the probability of being developed with the whole data in R. And then we used R-Bridge to push these data back to ArcGIS Pro. And we can take a look at the results in ArcGIS Pro. Back to ArcGIS Pro, the predictions from R have already been updated through R-Bridge. Here's a raster layer with our prediction results. Red is a high likelihood for development, green is a very low likelihood, and yellow is somewhere in between. Areas that are not color-coded are areas that were developed already in 2001. Let's take a little closer look. Here we can see our predictions. This is an area with a high likelihood of development. These are areas with low likelihood. What is interesting is that some of the areas we predicted with high likelihood have already houses in there. This is because our predictions are for 2016, while the satellite images are from 2019 or 2020. So in this cases, our predictions have already been confirmed.